Okay, so good morning, everyone. Welcome to yet another proof session. The first speaker is Noam Mazor, who's going to talk about on witness encryption and laconic zero-knowledge arguments.
Thanks, Jad, and thanks for coming to this morning session. I'm going to talk about joint work with Yanni and Rafael on witness encryption and laconic zero-knowledge. So let me start with the definitions. So witness encryption is a pretty strong primitive. It is defined with respect to some NP language L. And there are two algorithms, encryptor and decryptor. And there is some, the encrypt algorithm gets an instance for the language L together with a message. And it encrypts the message M with respect to this instance. Now we have two requirements, correctness and security. For correctness, we want that if the instance phi is in the language, then the decryptor, given a witness that the instance is in the language, will be able to decrypt, to get the message M. This is correctness. For security, we want that if phi is not in the language, then we will not be able to distinguish between an encryption of one message to the encryption of another message. So it's like a standard encryption scheme, but the security only holds for no instance, and correctness only holds for yes instance. It's not hard to see that for every language in P, we can trivially construct a witness encryption for it. But for NP, we basically only know how to construct witness encryptions from obfuscation. And witness encryption is like a pretty strong primitive, at least together with one-way function, it implies public key encryption. So this is witness encryption. This is one primitive. The second primitive is, So the question we want to ask is for what languages witness encryption exists and under what hardness assumptions we can actually construct them. Okay, so now this is one primitive. The second primitive is zero-knowledge proofs. Again, zero-knowledge proofs are defined with respect to some NP language, and we have a prover and verifier. The prover wants to convince the verifier that some instance phi is in the language. And the verifier is maybe randomized, interact with the prover, and in the end of the interaction, it decides if to accept or to reject. Now we have three requirements. The completeness says that if the instance is in the language, then the prover is able to convince V to accept with high probability. And I'm going to assume that the prover, given the witness, is efficient. For soundness, or actually computational soundness, we require that if he is not in the language, there is no efficient prover that is able to convince the verifier to accept with high probability. And the last property is the zero-knowledge property, which says that there exists an efficient simulator that simulates the view of the verifier in this interaction. So I'm only define honest verifier zero-knowledge. So I only want to simulate the honest verifier. And simulating the view of the verifier means to simulate the randomness of the verifier together with the messages it gets in the interaction. So this is zero-knowledge proofs. And another requirement we can ask for such a proof is to be laconic. So I would say that a proof system or argument system is laconic if the total communication from the prover to the verifier is order of log n bits. So the prover sends to the verifier at most order of log n bits. This is my definition of laconic. And again, a natural question we can ask is for what languages there is laconic zero-knowledge and from which assumptions we can construct them. Now, easy observation is that if we have a witness encryption to a language L, then we actually also have a laconic honest verifier zero-knowledge argument for this language. And the idea is that the verifier can just choose a random message of length L, when L is order of log n bits, encrypt it and send to the prover. And now the prover can, given the witness, can decrypt and sends M back to the verifier. And if phi is in the language, then the prover will be able to convince the verifier to send the right message. But if phi is not in the language, the best the prover can do is basically to guess the value of M because of the security of the witness encryption. And this is a laconic honest verifier zero knowledge protocol, and it also has other nice properties. For example, it's only have 2 messages. The prover is deterministic, at least in the sense that the verifier knows what the honest prover is going to send him in case that phi is in the language. The completeness error is negligible. The only error we have is that if the crypt algorithm of the witness encryption made an error. And for sourness, it's as optimal sourness in the sense that if he is not in the language, basically the prover can only convince the verifier to accept it, probability 2 to the minus L, because it basically needs to guess the value of M. So this is a very nice proof system. So we know how to construct laconic zero knowledge from witness encryption. And the question we ask in this work is witness encryption necessary? Can we construct laconic zero knowledge from a weaker assumption? And one work that I will talk about previous works later, but one work that make first step in showing that witness encryption or strong cryptography is necessary for laconic zero knowledge is the work of Berman et al. And they show that if you have a very laconic honest verifier statistical zero knowledge protocol, so if the prover sends log to the third and bits to the verifier, then together with a cryptographic hard language that I will define later what it means, you get public key encryption. So if you want laconic, very laconic, honest verifier statistical zero knowledge, you must assume essentially that public key encryption exists. Okay, so what are our results? So we showed that for every language in NP, the following are equivalent. One, there is a witness encryption for L. And secondly, there exists a laconic spatial honest verifier zero knowledge argument for the language L. So up to this modulo this spatial, that I will say what it is in a second, we basically showed that if you want to construct an honest verifier zero knowledge argument for a language L, you must assume that this language has a witness encryption. But there is this spatial which makes the result weaker. So what is a spatial honest verifier zero knowledge? So as I said, in zero knowledge, we require that there exists a simulator that simulates the view of the verifier, which means that it samples both the randomness of the verifier together with the messages the verifier sees in the interaction. In spatial honest verifier zero knowledge, the simulator gets its input, the randomness of the verifier, and it simulates the messages the verifier gets. So we can choose from outside, we can choose the randomness that the verifier sees in the interaction. And this is stronger than, of course, stronger than zero knowledge, but most of the zero knowledge protocols we have are actually spatial zero knowledge, but you can come up with examples which are not. So this is our results. And I will just say that if we start from proof system instead of arguments, if the proof is sound against any prover, not just efficient prover, then this is equivalent to statistically secure witness encryption. And also as corollary, we get that if L has laconic spatial honest verifier zero knowledge, then it also has 2 rounds laconic spatial honest verifier zero knowledge with optimal soundness, because this is what we get from witness encryption. And also, this gives that laconic spatial honest verifier zero knowledge for cryptographic hard language give public key encryption. Okay, so let me say a few words on previous works. And let me start with predictive arguments. So Faanio et al. Showed that predictive arguments for a language L is equivalent to witness encryption for L. So what are predictive arguments? So in the rest of the talk, I will only focus on 2 rounds protocols, but basically everything that I'm going to say is true also for arbitrary number of rounds. Predictive argument, two-round predictive argument is an argument system. When the verifier sends a message to the prover, a challenge, the prover sends an answer. And the premise is that there exists a unique answer from the prover to the verifier that will make the verifier to accept. And the verifier knows what this answer is. So the verifier knows what the unique answer from the prover that will make him accept. And Fanio et al. Showed that if you have such argument system, then you can construct from it a witness encryption. The construction is pretty simple. So if you want to encrypt a message M with respect to an instance phi, you can sample the first message of the verifier C together with the answer that the verifier knows that will make it accept. And then the encryption can be sent in C, and then computing a Goldreich-Levin hardcore predicate of A, and pad the message with this bit. And the property that the hardcore predicate has is that if you don't know the value of A, you cannot decrypt M. But an honest prover that knows the witness can find A, and therefore it can decrypt. So the decryption algorithm, given the witness, can just simulate the honest prover, find the value of A, compute the hardcore predicate, and then find the message. So this gives correctness. And the security basically holds because if phi is not in the language, there is no efficient prover that can convince the verifier that phi is in the language. So the prover cannot find A, so we cannot know what the value of the hardcore predicate is. And this proof, it's pretty simple, but it's pretty strong. And follow-up work used this in order to show that variance of zero knowledge implies witness encryption. For example, deterministic prover zero knowledge, a resettable statistical zero knowledge, and one-bit laconic argument, or arguments with one group element. Another work deals with laconic zero knowledge, and actually two works. So one is the work of Kermer and Shoup that basically showed that two rounds honest verifier zero knowledge with deterministic prover for cryptographic hard language implies public key encryption. And the second work is the work of Berman et al. That showed that very laconic honest verifier zero knowledge arguments for cryptographic hard language imply public key encryption. So what is a cryptographic hard language? A cryptographic hard language is a language in which it is very hard to distinguish between yes instance to no instances. So there are two distributions, D yes and D no, such that these two distributions are indistinguishable, but the D yes distribution is a distribution over yes instances, and the D no distribution is a distribution over no instances. And what this work says is if you have some kind of honest verifier zero knowledge for a language which is that hard, you can construct public key encryption from it. So let me show you the construction of Berman et al. So the idea is to take honest verifier statistical zero knowledge and to construct from it predictive argument. So we want to take this protocol and somehow change it such that the verifier will know a single A that will make it accept. And if we are able to do it, we can use the previous result in order to construct witness encryption from it. But the problem, of course, is that maybe there is no just a unique A that makes the verifier accept. And the public key encryption scheme actually looks very similar to witness encryption. The public key is going to be just an element in the language. The secret key is going to be a witness. And what we are going to do, in order to make the protocol predictive, in order to make A to be unique, instead of running the verifier to sample the first message C, we will run the simulator to sample C and A together. And since this is a statistical zero knowledge protocol, the distribution of C is exactly as the original distribution. And now the verifier knows a single A that makes him accept. So we will change the verifier such that the verifier will accept if and only if the prover sends him this specific A. And then we will get a predictive argument. But of course, if we just change the verifier that he will accept a single A, maybe the prover doesn't know which A the verifier is going to accept, and we lose soundness. So the solution of Berman et al. Is to send additionally to C a short hash of A, which will help the prover to find the right value of A. And the point is that given C, we can execute the prover with the witness to sample A from the right distribution. And we actually, not only that we can sample A from the right distribution, we can sample many times. And since the prover is laconic, the domain of the prover messages is small, we can fully understand the histogram of the distribution of the message A given the first message. So if the prover knows the histogram of the distribution, given the hash function of A, he can efficiently find the most likely A that the verifier has in his hand and to send it to the verifier. Now, this is a bit complicated because for one end, we want AA to be long enough to describe A fully. On the other hand, we want age of A to be short enough such that we will still have soundness, because if we just send A in the clear, the prover, of course, can convince the verifier he can learn A. So the analyze is a bit complicated, but this idea basically works. And from this reason that we need to choose the parameters of the hash function correctly, we only get that the proof system, it works when the proof system is this much laconic. Another problem with this proof system, with this construction, if you want to construct witness encryption, is that here we use the simulator to sample both C and A, but we only have a promise from the simulator when phi is a yes instance. So this is, we cannot use it for no instances, and therefore we only get public key encryption and we don't get witness encryption. So now I will tell you a bit about our approach. So we consider, instead of considering statistical zero knowledge, we're considering a spatial honest verifier zero knowledge, which means that we have this strong simulator that gets both the instance and the randomness of the verifier. And the idea is that now, using this simulator, the verifier, every time that we run the simulator with the same random string, it simulates the verifier with the same randomness, which means that the verifier message is the same every time we execute the simulator with the same random string. The prover message can be changed, but the verifier message is always the same. And this also helps because we choose the randomness of the verifier. The first message is distributed according to the real distribution of the verifier message, even if we start with a no instance, because we have the ability to choose the randomness of the verifier, so we can compute the first message of the verifier using the randomness. So now we have a promise also for no instance. This is one reason we are able to get witness encryption. The other thing that we have in this protocol using this simulator is that now also the verifier has the ability to run the simulator many times. And this means that also the verifier knows the histogram of the distribution of the prover message given the first message of the verifier. So now both the prover and the verifier agree on the same distribution of the next message given the previous message. And this allowed them to basically do correlated sampling in order to make this protocol unique. So what we are going to do, the way we are going to change the protocol, is that the verifier is going to just choose a random number between 0 and 1 and send it to the prover together with C. This, of course, cannot harm soundness. We just add random number. And then the prover and the verifier will use this number to sample the value of A together in a correlated way. And the idea is that if we have this histogram, then we have like segment for every possible answer of the prover, and the like area below the histogram is the probability to sample this specific message. The total area below the histogram is of course 1 because this is a distribution. The verifier given P can just find the point on this line such that the area below the histogram up to this point is exactly P. And if this point is in the segment relates to A3, it will only accept if the prover sends A3 as an answer. And now the prover has the same histogram, so he can do the same, and then they will agree on the same value. So this gives us a predictive argument. And this actually works also in the case that the distributions are only statistical close, which is actually what we get from the proof system. And this gives us witness encryption protocol. Okay, so to summarize, we showed an equivalent between witness encryption and laconic spatial honest verifier zero knowledge arguments. Open questions then, maybe we don't need the spatial zero knowledge. Maybe we can do it from laconic honest verifier zero knowledge, or actually maybe we can do it from any laconic proof system or argument system. This is one open question. And the second is which languages have witness encryption and under which assumptions. Thank you.
Any questions?
Hello. A nice talk. I wanted to ask, so you use the special honest verifier zero knowledge, and you have this open question, but then you would kind of, like if you answer the open question, you would get that special honest verifier zero knowledge and non-special are equivalent. Right? This is kind of surprising. So maybe it tells me that I don't expect this to be true.
Right. Yeah, but when the argument system that the prover is very laconic if it sends only one bit, then actually we know that this is true.
Laconic.
So it might be the
So
case.
maybe for laconic protocols, special and non-special are equivalent, but in general, they're not. Okay, thanks.
Okay, let's thank the speaker again. Be a Zoom recording, unfortunately. And it's going to be about trait one, statistical, non-interactive zero knowledge. And I'm actually not sure who the speaker is, so we'll discover in a short moment.
Hello everyone, I'm Akshay Ram Srinivasan and I'm going to talk about Rate 1 Statistical Non-Interactive Zero Knowledge. This is based on joint work with Pedro Branco and Nico Dotling. Let me start by recalling zero knowledge proofs. In this setting, we have a prover and a verifier, and the common input to both parties is a statement X. The prover wants to convince the verifier that the statement X belongs to an NP language L. For this purpose, the prover and the verifier interact with each other by sending messages, and at the end of the interaction, the verifier either accepts or rejects this interaction. We want this interaction to satisfy three properties. The first is completeness, which states that the verifier accepts if X belongs to this language L. The second property is soundness, which requires the verifier to reject with overwhelming probability if X does not belong to the language L. Typically, soundness is required to hold against computationally unbounded provers, but if this requirement holds only against PPT provers, then we have a computational notion of soundness, and such proof systems are called arguments. The final property is zero knowledge, which states that any PPT verifier does not learn anything from this interaction except for the fact that X belongs to this language. If this zero knowledge property holds against computationally unbounded verifiers, then we get statistical zero knowledge. In this talk, we are interested in the non-interactive version called as non-interactive zero knowledge. So in this setting, in addition to the common input X, the prover and the verifier are provided with a common reference string sampled from some distribution. So using this common reference string, the statement X and the witness W, the prover generates a message pi, which is also called as the proof, and sends it over to the verifier. The verifier now runs a verification procedure on this proof, and this verification procedure either accepts or rejects this proof. Again, we want this proof system to satisfy completeness, soundness, and zero knowledge property. It's not hard to show that if L was NP complete, then we require either the soundness or the zero knowledge property to be computational. Suppose we have a proof system that satisfies computational zero knowledge property. This means that the zero knowledge property relies on a computational hardness assumption. If this assumption turns out to be broken at a later point of time, then given the proof pi that the verifier received from the prover, some non-trivial information about the witness could be learned. However, if this proof system satisfies statistical zero knowledge, then we get some sort of everlasting security. In contrast, the soundness notion is required only at the time of generating this proof. So as long as the computational assumption that underlies the soundness criterion has no better attacks, we can continue to use this proof system. So as a consequence of this argument, we want our proof system to satisfy statistical zero knowledge so that we get some sort of everlasting security, and we have to rely on computational soundness. In fact, we would consider a stronger notion of computational soundness called argument of knowledge. So suppose a PPT prover generates a proof pi that the verifier accepts. The argument of knowledge property requires the existence of an extractor that takes its proof pi and outputs the underlying witness W for this statement X. Argument of knowledge is a stronger property than standard computational soundness, and it is in fact desired in many scenarios. So we will consider argument of knowledge property. The default NP-complete language that we'll consider in this talk is circuit SAT. So here the instance consists of a Boolean circuit C along with a string X. The witness is another string W such that the output of this Boolean circuit on X comma W is equal to 1. The main goal of this talk is to minimize the proof length. So specifically, we want to answer how small can this pi be. The prior work of Gentry and Wicks and the recent work of Campanelli et al. Gave lower bounds on the size of this proof for argument of knowledge systems where the reduction makes black box use of the adversary. So specifically, under the exponential time hypothesis, they show that any argument of knowledge must have the proof size to be at least a constant times the size of the witness. So this shows that any natural construction of Nizic argument of knowledge cannot have sublinear proof size. On the positive side, the work of Gentry et al. Gave a construction of a Nizic proof system where the size of the proof was just witness plus poly in lambda, where lambda is the security parameter. So this relies on the assumption that fully homomorphic encryption exists, plus Nizics, where the proof size could be an arbitrary polynomial in the witness size. And the reduction makes black box use of the adversary. So we call such proof systems to be rate 1 because the ratio between the size of the witness to the size of the proof approaches 1 asymptotically. Unfortunately, the work of Gentry et al. Only achieves computational zero knowledge and could not achieve statistical zero knowledge. So the main question we are interested in this work is, can we achieve rate 1 proof systems that satisfy statistical zero knowledge? In this work, we give such a construction assuming sub-exponential hardness of either k-lin assumption on groups with efficiently computable bilinear maps, or the DDH assumption, or the LWE assumption. And the size of the proof system, in our work is witness plus some witness to the epsilon times poly in lambda for some small constant epsilon. And this proof length has rate 1 because the ratio between the size of the witness to the size of the proof approaches 1 in the asymptotic sense. In fact, the sub-exponential hardness assumption in our theorem is inherent due to a work of Pass from 2013 concerning statistical non-interactive zero knowledge proofs. Okay, so in the remaining time, I would give you a high-level overview of our approach. So the prover on input instance, which consists of C, X and the witness W, first generates the computational tableau in a step-by-step manner. So let T1 be the snapshot of the computational tableau after evaluating the first gate in the circuit. Similarly, T2 is the snapshot of the computational tableau after evaluating the first 2 gates and so on. So T subscript C is the entire computational tableau. So the prover takes in these snapshots and hashes each one of these snapshots into a short hash using a Merkle tree. So it then takes in these digest and hashes them further using a special somewhere extractable hash function to obtain a short digest H. So this special somewhere extractable hash functions is required to satisfy certain other properties to achieve statistical zero knowledge, but I wouldn't be going too much into the details for this talk. So the proof in our construction consists of a special commitment to the witness. Again, we require this commitment to satisfy certain special properties for achieving statistical zero knowledge. Let me not go into the details. Along with the digest that is obtained by applying the somewhere extractable hash function on the Merkle digest on the snapshots. Of course, the main problem with this approach as of now is that how do we prove that this witness was in fact used to generate these computational Tableau snapshots? And how do we show that the output of the final wire in this Boolean circuit carries 1 when we run on this witness W and the instance X? So we need some sort of consistency proof. So for this purpose, we make use of a tool called as batch arguments. So let me explain what a batch argument is. So a batch argument takes in a batch of k NP statements along with the corresponding witnesses and compresses these witnesses into a short proof pi. We require the size of this proof to only grow polylogarithmically in the size of the batch. So specifically, it grows as polynomial in security parameter, size of one of these witnesses, and logarithmic in the batch size. And verifying this proof somehow attests that each one of these statements belong to this NP language. And we know how to construct such batch arguments from learning with errors, from bilinear maps, as well as sub-exponential DDH. Okay, so let's see how to use these batch arguments to prove consistency between the commitment to the witness and the digest H. So for this purpose, we construct C NP statements. At a high level, the jth NP statement attests the fact that the jth gate in the circuit was computed correctly. So to give a bit more detail, let's say that the jth gate takes in wires I comma j as inputs and the output wire is k. The relation corresponding to the jth instance takes as input the following as the witness. So it takes in the openings to Hg and Hg minus 1 with respect to this digest H. And it also takes in the openings to the values carried by wires I and j in the tableau. So suppose I or j was an input wire corresponding to the witness, then this opening is with respect to the commitment to the witness. Otherwise, it is if it is an internal wire, then it is an opening with respect to the digest Hg minus 1. And finally, it also takes us as another opening corresponding to the kth wire in Hg minus 1. Note that kth wire has to be unset at this point. So the opening should be to the unset value denoted by bot. So this takes in all these things as the witness. It checks whether all the openings are correct. And if it checks whether Hg is obtained from Hg minus 1 by setting the kth wire value to be equal to g of alpha comma beta. That is the output of this gate. And note that this is efficiently checked if one also takes in the openings to the wire k in Hg minus 1, and this is a property of Merkle tree. And finally, if G corresponds to the final gate, then it checks whether the output is 1. Okay, so this is what the relation corresponding to the G statement checks. So we now take in all these witnesses and compress these witnesses using a batch argument to obtain this proof pi. And the proof in our that is sent by the prover consists of the commitment to the witness, the digest H, and the batch argument pi. So let's verify the size of the proof in a construction. We actually make sure that the special commitment to the witness satisfies has the size which is witness plus witness to the epsilon times poly in lambda. We also ensure that the size of the digest is just poly in lambda, and the size of the batch argument using some clever tricks is somewhat fixed to be some witness to the epsilon times poly lambda comma log c, because log c is because the batch size is c. Okay, so this is the size of the proof, and that is why we achieve rate 1. So let me give you some very high level idea behind the argument of knowledge. So firstly, we make sure that the commitment is extractable, and using the extractor for the commitment, we extract the candidate witness. But the main question is, how do we ensure that the extracted witness is indeed valid? And for this purpose, we make use of the soundness of the batch argument. So recall that this digest H is obtained by using a special somewhere extractable hash on the Merkle digest of each snapshot of the computational tableau. So suppose we ensure that the digest at the end of the jth gate computation was consistent with the extracted witness. Then the collision resistance of Merkle hash ensures that all the gates until the gate G were computed correctly. And now we can rely on the soundness of the batch argument to show that Hg plus 1 was consistent with the extracted witness. So this is a very high level overview, and now we can use induction. Okay, so I wouldn't have time to go into the details of how we prove statistical zero knowledge, and I would encourage you to look into a paper for the details. So to conclude, we gave the first construction of statistical Nizhik argument of knowledge with rate 1 from standard assumptions. And some interesting open questions are to get rate 1 Nizhik from factoring. This is not known. Even if the system just achieves computational zero knowledge, this is not known. And another interesting question is to get computational Nizhik proof with rate 1 without using heavy hammers such as fully homomorphic encryption, which was needed in Gentry et al.'s work. And that's it. Thank you for your attention.
Okay, so the next talk is going to be about how to share an NP statement or combiners for zero knowledge proofs. And the authors are Benny Applebaum and Eliran Cohen. And unfortunately, we're also going to have a video.
Good morning. I'm going to tell you a little bit about this new notion of sharing an NP statement and how it is related to the problem of combining zero knowledge proofs. And this is joint work with my student, Eliran Kahlon. So let me start with the reader. You want to prove a theorem in class, but you don't want to give too many details. You want to prove it in zero knowledge. And at your disposal, you have 3 TAs. The problem is that only one of them, one of them is not sound and one of them is not zero knowledge, and you don't know who is who, right? More generally, we can think about the problem of combining many zero knowledge proofs, say many faulty components, where only majority of them are sound, the majority of them are zero knowledge, and our goal is to kind of somehow combine them into a single system that achieves both soundness and zero knowledge. And ideally, we want this combiner to be interactive and black box in the code of these provers or TAs. And currently, we only have partial solutions that either don't scale with the number of components, so they work only for a small number, say a constant number of TAs, or require a more than honest majority. So let's keep this problem in mind. So in this talk, I'm going to present this notion of secret sharing for an NP statement. I believe that this is a very cool notion, and I'll try to argue that this is a cryptographic analog of standard NP reductions. Then we're going to show that you can use this notion in order to get a very strong form of zero knowledge combiners, and even use it further in other contexts and get several applications in the domain of zero knowledge proofs and secure multi-party computation. And finally, we'll show how to realize this creature based on a new funky or funny notion of information theoretic MPC that we'll present. So this is the high-level plan. And I want to say that coming up with the right definition of this notion of MPC secret sharing is somewhat subtle. And you want on one hand to get to have something which is strong enough for the application, on the other hand, weak enough so that you can realize it. And this is going to be a somewhat delicate task. And maybe one of the key contributions of this work is to suggest such a definition that works in both ways. So we're going to spend some time on trying to understand what is the right notion of secret sharing for an NP statement. So let's start with standard secret sharing. So T out of n secret sharing, we have a bit or a field element, data item, and we map it into n shares, such that if you have T of them, you can recover the secret. But if you have less than T, say T minus 1, you learn nothing on the secret in information theoretic way. So we want to extend this notion to the context of NP statements. This was originally done by Goyal et al. And we're going to use slightly different formulations, and I refer you to the paper to read about the detailed comparison between these two notions, and the difference matters. So anyway, so we want to share an NP statement. So let's say that instead of holding a data item, we are holding a circuit set instance. Okay, so this is a circuit F and an assignment satisfying assignment X. So I want to map it to map the circuit into n circuits, n instances F1 up to Fn. And this is going to be a deterministic mapping that everyone can apply. And we're going to have a randomized mapping, a randomized witness mapping that takes this witness, the assignment, and maps it into n assignments, y1 up to yn. And we want similar properties to the properties of secret sharing. So if X satisfies F, then these Y's should satisfy all the Y's. Okay. We want privacy. So what does privacy mean? So in secret sharing, it means that if you see few shares, you learn nothing on the secret. So here, let's say that you see less than T of the assignments, say 2 assignments, then it gives you no information on X. And we're going to formalize it by using a simulator. So there exists a simulator that looks only on the instance and generates say any pair of these assignments or any T minus 1 subset of this assignment, such that the distribution of these guys is going to be identical to the distribution that is obtained by applying this witness mapping on an assignment. Okay, so this is privacy. Recovery means that if you see at least T pieces of data, right? I mean, at least T satisfying assignments, then it means that F is satisfiable. And again, we want something stronger. So we want an efficient decoder that looks at these T satisfying assignments and recovers the satisfying assignment from F. So this is quite intuitive. The problem with this definition is that you cannot realize it unless P equals to NP. And roughly speaking, the reason is that you can use the simulator to generate all these YIs, then use the decoder in order to get X, and then check whether X satisfies F. So we have to change the definition to slightly relax it, and the idea is to introduce some correlation between these Fs. So we cannot kind of require Fs that are independent, right? We want some correlation. The correlation is going to be achieved by requiring overlap between these variables. So we're going to have one set of this joint variables, y1 up to ym. And each of these statements or circles is going to look at some of these variables. Okay. And now we require the same properties as before. So correctness means that if X satisfies F, then Y satisfies all these Fs, Fi's. The privacy means that I can simulate based on F. The partial assignment corresponds, say, to any T minus 1 of these assignments. And the correctness means that if I have something that satisfies at least T of these statements, then I can recover the satisfying assignments for F. Okay. So another way to kind of state the above thing is instead of talking about one global assignment, let's talk about partial assignments. Right? So we have n partial assignments, one for each of these Fi's, and these guys should be pairwise consistent. So if y keeps the first variable assigned and y2 also keeps this first variable assigned, then these two guys should be consistent. So all these partial assignments are consistent with one global assignment. And it's very clear that if F1, right, I mean, if some variable does not affect F1, then I can keep it unassigned. But in fact, I'm going to further relax this notion, and I'm going to allow F1 to depend on variables that I'm going to allow the partial assignment to unassign variables that affect the output of F1. So even if the 10th variable here affects the output of F1, I can keep it unassigned. Okay? And this is an artifact of the constructions that we have. I don't know whether this relaxation is necessary. But anyway, once I use this relaxation, I have to extend the logic of the standard Boolean logic to handle partial assignments. And the way that I'm going to do this extension is going to be in the natural way. So when I'm going to evaluate a circuit on a partial assignment, I'm going to use the following rules. So 1 or unassigned is 1, 0 and unassigned is 0. And otherwise, when I have unassigned variables, the output of the gate is going to be unassigned. And I'm going to say that the circuit is satisfiable if its output is 1. Okay. Again, this is relaxation. We don't know whether it's necessary. It will be very interesting to show that it is necessary for the constructions. So our main theorem shows that for every T and N, you can get T out of an NPSS, information theoretically and efficiently. Previously, as I mentioned, Goyal et al. Had their own notion of MPSS. It was computational, and they were able to construct only n out of n MPSS, or MPSS with a gap between the privacy threshold and the correctness threshold, like third versus two-third. So once we have this theorem, we show that you can use it to get a strong notion of zero-knowledge combiners. And in particular, we're going to get what's known as multi-string NISC. I will explain this application in a minute. Also construct multi-verifier offline online zero-knowledge proofs. This is something that was recently studied in several papers, this notion, and this is, in a sense, the best achievable construction that you can have. And finally, by using this tool, we can get a general MPC in the honest majority setting that is secure against the active adversary with guaranteed output delivery in an optimal number of rounds. This is 3 rounds. And we can get it based on the minimal assumption, the existence of one-wave function. And this kind of object, a 3-round actively secure MPC, was studied in several papers. And just for comparison, just a decade ago, the only known construction that we had was based on the threshold fully homomorphic encryption, NCRS and NISC. And now we went all the way down from this strong assumption to the minimal assumption of one-wave function. So this is a kind of a rare example where in a single decade, you go all the way down. Good, so I don't have time to talk about all these applications, but I'm going to focus on one of them, this multi-string NISC application. So in non-interactive zero-knowledge proofs, we have a prover and verifier, and we have both have access to a CRS, right, common reference string. As long as the reference string is okay, right, we have soundness and zero-knowledge. However, if the CRS is bad, then soundness can be violated, and also zero-knowledge can be violated. And the standard solution is to distribute the trusts. We'll have a bunch of authorities. We'll use, say, MPC protocol to jointly generate the CRS. And we have the guarantee that as long as we have honest majority, then the CRS is good. Problem is that this solution is typically expensive. It's interactive. It typically has high cost in communication and computation. And this is especially true for structured CRS. Think about generating RSA public parameters. So Gross and Ostrowski suggested a very elegant solution to this problem. They suggested a way to distribute the trust in a non-interactive way. So they have this notion of multi-string NISC. So in this model, each party generates its own CRS. They don't talk to each other. The prover and the verifier both see all these CRSs. And the proof has the property that as long as we have honest majority across the CRS, we have soundness and zero knowledge. And somewhat miraculously, Gross and Ostrowski showed that if you have NISC over uniform CRS, then you can upgrade it and get multi-string NISC, right? Assuming also the existence of one-wave functions. So this is a very cool result, and the natural question is what can you do if you have NISC which does not use a uniform CRS, it uses a structured CRS. So we solved this problem, and we prove an analog result to the result of Ostrowski, of Gross and Ostrowski, show that given NISC over arbitrary CRS, possibly structured, you can get a multi-string NISC based on the existence of one-wave functions. Right, and the proof is actually very simple. You'll see it in a minute. And it's simple enough so that the transformation preserves many useful properties, such as statistical soundness, proof of knowledge, succinctness, and so on. And the previous transformation didn't preserve this property. So this is another cool feature. So let's see the proof. So each of these parties generates its own CRS. The prover is going to take its circuit set instance and use the MPSS to generate n instances. And we're going to set the threshold such that we have privacy against minority and recovery for any majority. And now the prover is going to take its assignment and generate all these partial assignments. It's going to send a commitment to the global assignment and n proofs, where the ith proof is with respect to the ith CRS, and the ith proof says that there exists yi, a partial assignment that satisfies the ith predicate and is consistent with the global commitment. Okay. The verifier is going to accept the new proof if all these proofs pass verification. So let's argue soundness and zero knowledge. So if the prover is cheating, still there is an honest majority among the CRS, so he has to cheat to find partial assignment over majority of these predicates, right? And by the recovery properties, finding satisfying assignment for a majority of the predicate means that the original F is satisfiable. So if we pass verification, we know that F must be satisfied. For zero knowledge, imagine that the verifier collaborates with the minority of these authorities. And let's say that these authorities generate a CRS such that the proof, right, completely, the corresponding proof completely leak the corresponding witnesses. This is still fine because it leaks only a minority of the witnesses, and we know that we have privacy against minorities. Okay, so that's the proof, and you can see that it is very robust, makes a very general use of the commitments. So how to construct MPSS? So the key idea is to define this new notion of T out of n MPC. The definition is somewhat tricky, so let me show you an example of 4 out of 5 MPC. So we have 5 parties. We want a perfect passive correctness. This means that if everyone is honest, then the output is correct. That's kind of trivial. We have this threshold, and we think if we look at small coalitions, right, coalition below the thresholds, in our case, this is kind of triplets, then these coalitions learn nothing from the computation, right? So formally, we have perfect passive privacy against T-1 size coalitions. On the other hand, if you look at 4 parties, then they essentially know everything, okay? Just like in the secret sharing domain. So 4 parties learn everything about the output in the sense that even an active adversary that knows everything, knows the inputs of these parties and the randomness, still he cannot force the wrong output, okay? Specifically, if their corresponding inputs already fix the output of the function to 0, then even an active computationally onboarded adversary cannot force these guys to output 1. So this notion is somewhat non-standard, and existing protocols do not satisfy it. So we have to construct new protocols that satisfy it. And the way that we do it, we give a simple direct construction from 1 out of 2 MPC and 0 out of 2 MPC. This is actually trivial. And then we extend it to the general case by using the techniques of player virtualization and the fact that the threshold function has a polysize monotone formula. And I know that this is kind of vague. Look at the paper and see the details. Once we have this MPC, we transform it into T out of n MPSS. And for this, we use a variant of the MPC in the head transform. And we have to be careful because we care about exact threshold. And for this reason, we have to be very careful about the way that we use these OT hybrid channels. And it turns out that the use of OT channels translates to this use of partial assignments that I talked about previously. So let me summarize. We have this new notion of information theoretic MPC with a threshold behavior for privacy and correctness. We'll show again that virtualization is a very powerful tool. We present information theoretic secret sharing for an MP statement. And in this domain, there are several interesting open questions, and we'd like to see more application. And let me get back to the beginning of the talk where I said this is kind of a cryptographic variant of MP reduction. And the reason is that we take a circuit sat instance, we map it into multiple instances, so that the satisfiability of the original instance boils down to the satisfiability of, say, T out of these instances. But if you look at T-1 of the instances, then it gives you no information on the satisfiability. Okay? We use this notion to get all these results, including this nice 3-round honest majority actively secure MPC from a one-way function. And I have to say that we thought a lot about this problem before, also together with Arpita Patra, and we couldn't solve it. And eventually we had this crazy route that kind of starts from information theoretic MPC and eventually leads to this thing. And I think that we couldn't do it without having here the right abstraction. And maybe there's a general lesson here about the importance of abstractions and how crucial it is for us as a community to come up with the right notions. So thank you.
Okay, so the last talk in this session is going to be about Nizic amplification via leakage resilient secure computation, and it's by the same authors, and I assume Ben is gonna give the talk.
So hello again. In this talk, I'm going to tell you about NISQ amplification and about leakage resilient secure computation. And this talk is also based on a joint work with Liran Kahlon. So security amplification is a classical theme in cryptography and complexity theory. And the main goal is to take a weak cryptographic primitive whose error, measured as the probability of a successful polynomial attack, is almost 1, right? It's 1 minus 1 over poly. So you can almost surely break this primitive and turn it into a strong cryptographic primitive whose error is only negligible. That is, you can hardly break this primitive. Okay, and there are quite a few canonical examples that we all know in this domain. So, for example, the example of weak one-way functions that can be converted into strong one-way functions by using repetitions. This is due to Yao. And more generally, typically when we have search problems, we can use repetitions to amplify them, for example, in signatures. Another famous example is the example of distinguishing problems, for example, weak pseudo-random generator that can be turned into strong pseudo-random generator either via the use of XORs, the XOR lemma, or via the use of randomness extractors. Why should we care about security amplification? Well, there are several reasons. One reason is that in many cases it's much easier to construct a weak primitive and then upgrade it into a strong primitive as opposed to directly construct a strong primitive. And the famous, maybe the most famous example is the construction of pseudo-random generators on one-way functions that goes through several weak variants of PRGs. Another reason to care about these questions is that it gives us better understanding of our basic security notions. In particular, it tells us how different security notions are preserved under different manipulations. And finally, and maybe most importantly in retrospect, is that these type of questions lead to very powerful and useful tools. I already mentioned randomness extractors that were invented in this context, and there are many other tools that were also invented by studying questions about security amplification. Good, so today we're going to talk about NISQ amplification, and this problem was first raised by Goyal et al. And here we are given a non-interactive zero-knowledge proof for NP that has some errors. So it has alpha soundness error and beta zero-knowledge error, where here the error measures the deviation of the simulator with compared to the real interaction. And the question is that if we have such a NISQ with some errors, can we reduce the errors to be negligible? And if you think about it a little bit, you'll see that this is impossible if the total error is 1. Okay? For example, we can have a NISQ, such a NISQ whose total error is 1 unconditionally, and therefore we cannot hope to turn it into a full-fledged NISQ. And one example of such a trivial NISQ is a NISQ in which, with probability beta, we completely leak the witness, and otherwise we keep it secret. We just say nothing, and you can see that this thing has exactly alpha soundness error and beta zero-knowledge error. So we have to assume that the total error is smaller than 1, or in other words, that there is some level of security. And perhaps the most extreme case is to assume that we have a weak NISQ whose total error is almost 1, right? It's bounded away from 1 by 1 over poly, just like in the case of one-way functions, and turn it into a strong NISQ whose total error is negligible. Right? So that's the question of taking a weak NISQ into strong NISQ. So what do we know about this question? So in the original paper, Goyal et al. Suggested a transformation that takes a moderately secure NISQ, whose total error is bounded away from 1 by a constant, or in other words, it has some constant security level, and they show that you can turn it into a strong NISQ. Now, this paper has many beautiful ideas. Unfortunately, the proof of this theorem turns to be flawed, and Bitansky and Geyer fortunately showed that this can be fixed, and they presented a different transformation that achieves this result. Still, the basic question of taking weak NISQ and turning it into strong NISQ remains wide open. And that's exactly what we do. We prove a strong NISQ amplification theorem. That is, we can take a weak NISQ that has error which is almost 1, right? And take it all the way up to a strong NISQ where the error is negligible. And our proof is very robust. It holds in many settings in a unifying way. For example, the canonical setting where the soundness is statistical and zero knowledge is computational, all we need is one-way functions. For other settings, we need slightly stronger assumptions. And as a bonus, we can also preserve the succinctness of the proof system if we are using, if we have a collision-resistant hash function. And this is nice because in previous transformations, we didn't know how to preserve statistical or succinctness, even if we start from a moderately hard NISQ. So before we're talking about the proofs, let me mention two challenges that arise in this context of NISQ amplification. The first problem is that we want to simultaneously amplify soundness and zero knowledge. Right? This is very different from the case of one-way functions where we have only one kind of security property that you want to amplify. And the existing solutions use the following template. They construct some sort of soundness amplification, typically based on repetitions. Then they have to come up with some sort of zero knowledge amplification, and they iterate between these two procedures a constant number of times. In fact, these templates go back to the work of Sahai and Vadan on statistical zero knowledge proofs. And let me point out that the fact that they do it constant number of times is actually very important. We'll get to this point back later. So the second problem is that even zero knowledge amplification alone is non-trivial, right? It's not clear how to do this. We don't have the right tool for this. And know that this is a distinguishing problem, right? Our goal is to amplify the distinguishing advantage between the simulation and the real interaction. So Bitansky et al. Did the following clever idea. They show that this problem reduces to the problem of pseudo-randomness amplification. So they use the weak NISQ in order to realize some sort of weak pseudo-random generator with an extra hidden bit property. Let me ignore it for a second. Then they use the standard amplification tools of pseudo-randomness like extractors in order to get strong PRG with this, again, additional property. And finally, they use this PRG in order to realize the hidden bit model. And then they use an off-the-shelf construction of NISQ in this model due to FLS. Note that this construction is completely kind of independent of the original construction, right? And therefore, even if the original construction had statistical zero knowledge or succinct properties, now we lose these properties because we use this off-the-shelf NISQ. Goyal et al. Had a different approach, and this approach, as I said, fails, but still it's very useful, and we're going to use a similar approach. So let me explain it. They suggested to use zero knowledge combiners, right? And the zero knowledge combiners, they constructed them based on the N out of N PSS. This was the subject of the previous presentation. So in a sense, we are going to fix their failed approach, use a fancier object here, fix the bug, and also at the same time we'll be able to amplify soundness and zero knowledge simultaneously. Okay, so let's talk a little bit about the combiners. In the setting of combiners, we have n candidate constructions. Let's back to the TAs. So we have n TAs. We know that A of them are not sound and B of them are not zero knowledge, and we know that A plus B is at most n. In the setting of amplifier, we have a single TA, which is kind of a weak TA. Right? It makes soundness error probability alpha. It has some zero knowledge deviation with error beta. Right? In both cases, of course, we want to get a single NISQ construction, right, out of these things. But the situation seems somewhat different. Still, we could ask, I mean, can't we move from this notion to this notion? Right? Can we reduce the problem of amplifier to the problem of combiners? And there is a naive attempt to do this. Let's sample many copies of this TA, right? And we know that roughly alpha fraction of them are going to be to violate soundness, and the beta fraction of them are going to violate zero knowledge. And now we can use our combiner to solve this problem. Now this approach does not work, and let's see why. The problem is that the event of zero knowledge failure depends on the witness. This means that even good instances that for which we had the success still leak information. The fact that the event happened here, or did not happen if this is the bad event, this already leaks information about the witness. Now it turns out that this leakage information can be formalized, and indeed the work of Goldreich and Petrank showed that in such a situation you can simulate the interaction with good distinguishing advantage, assuming that the simulation itself is given some bounded leakage on the witness. So this suggests the following natural strategy. Let's try to build leakage resilient combiners and then use them as amplifiers. So that's exactly what we do. So this is a slide from the previous talk. Remember, in the previous talk we constructed the zero knowledge combiners based on secret sharing for NP statement, and this creature was constructed based on this funny threshold type of MPC protocols. So we're going to follow a similar route, but now we want NISC amplifiers, and for this we'll need secret sharing for NP statement with additional leakage resilient property. And for this, we'll have to construct these funny MPC protocols with leakage resilient feature. Okay, so this is the rough template of the proof. And there are several annoying technicalities. One problem is that the leakage function is not efficiently computable. So this does not make any problem as long as your hybrids are information theoretic. But once you have computational steps, then this can be a problem. Specifically, the use here of computationally hiding commitments is problematic. And one solution is to replace this commitment with statistically hiding commitments. That would work, but then we'll have to rely on assumptions that are stronger than one-way functions. So instead, we use trapdoor commitments. These are commitments that have a trapdoor mode, which is statistically hiding, and we can construct them based on one-way functions by following the ideas of Feige and Shamir. And let me say that compared to the previous work where we moved from secret sharing for NP to combiners, where this step was very, very simple, the current step is much more complicated and the proof is subtle. Another annoying technicality is that all our constructions have inverse polynomial error instead of negligible. So this starts at the top here in the constructions of MPC. And we inherit this 1 over poly error all the way down to the amplifier. So we need another second NISC amplifier that takes us the last mileage, right, from 1 over poly to negligible. We could use for this the amplifier of Bitansky et al., but then we wouldn't get this succinctness property and statistical zero knowledge. So we'll have to present our own amplifier. And for this, we know that we show that actually combiner suffices. So when the O is so small, you can just use combiner. And this thing already have been observed in other contexts, and we extend this phenomena to this setting. And to prove this theorem, we'll have to prove a new variant of the XOR lemma. So I will not have time to talk about all these steps. Please take a look at the paper. But let me mention that when we construct this funny MPC, along the way we also construct a standard MPC, which is leakage resilient, and I want to talk about this result for the last few minutes of this talk. So leakage resilient MPC, so we are thinking about the setting where the adversary is computationally unbounded and passive. And as usual, it can corrupt some of the parties, so it gets to see all the view of these corrupted parties. But in addition, it gets some bounded leakage from each honest party. So say B bits of a leakage, where B is some parameter. And this leakage can be computed by applying an arbitrary leakage function on the view of this honest party. So what do we know about this model? So existing solutions suffer from several drawbacks. One problem is that we have to rely on n-wise correlated randomness. So for example, we have to assume that the parties start with random points that all lie on a low degree polynomial. So that's a very strong form of setup. And let me remind you that if we don't care about leakage resiliency, like in the standard model, we can get such protocols only based on pairwise correlations, right? Like OT correlations. So this is a strong drawback. Another problem of existing solution is that they only achieve bounded resiliency, so they can the adversary can corrupt some constant function of the parties, say I don't know 90%. Or alternatively, we have solutions that work for arbitrary number of parties, but they don't scale well with the number of parties. So they have exponential dependency in number of parties, and therefore they are restricted to a small number of parties. On the positive side, these solutions can tolerate a large fraction of a large number of correlated leakage bits. So you can set the leakage bound to be polynomial in the security parameter. Now in this work, we show that you can overcome some of these limitations. For example, to begin with, we show that this is indeed possible only with pairwise correlations, like OT correlations. We can achieve security against unbounded collisions, so even if the adversary corrupts everyone except for one party, then the protocol is secure. But we pay for both features by only allowing a relatively small amount of leakage, so the leakage is only logarithmic in the security parameter, and as I already mentioned, we have inverse polynomial security error. So how does the protocol look like in a very sketchy way? So we start by constructing a leakage resilient protocol for two parties. Okay, and for this we use leakage resilient secret sharing schemes. Then we use a protocol in the standard model, like in the standard hybrid model, which is not leakage resilient. So this protocol can be based, for example, on the GMW protocol. And then in order to construct a leakage resilient protocol over these 6 parties, what we do is that we are going to run this GMW protocol in a virtual way. So we let each of these 2 parties emulate one GMW party, right? And this emulation is going to use the 2 parties leakage resilient protocol. Okay? So this is roughly the idea. I'm hiding several details here, but that's the high-level approach. So again, virtualization. We have to rely on a strong notion of leakage resiliency in order to allow a composition. And remember that in this GMW protocol, we make use of OT channels, and we have to find a way to emulate these OT channels, and this is the most sophisticated part of the protocol. For this, we have to use 2 levels of secret sharing schemes with different security parameters. And eventually, this use of this compilation of OT calls lead to a complexity which goes polynomial in the size of the domain of the shares. And for this reason, we're restricted only to a relatively low level of leakage and to this 1 over poly security. So it will be very interesting to get rid of this limitation. So let me conclude. We showed that leakage resilient MPC can be realized only with the pairwise correlations. And as I mentioned, it will be nice to get here a negligible error. We presented this notion of leakage resilient MPSS. I didn't talk about it this much, but you can look at the paper. And finally, we're able to use these tools in order to get an amplifier that goes from weak NISC into strong NISC. And as I mentioned, as a bonus, we preserve the succinctness and statistical security. So let me end up by taking another look at the previous approach. So remember that we have a constant number of levels of soundness amplification, zero knowledge amplification, and so on. And if you look closely, you will see that implicitly these previous approaches implemented a constant depth circuit for approximate majority, right? An AC0 circuit. And because this was only approximate majority, they get only moderate amplification. Now, why do they have to do a constant number of layers, right? I mean, maybe you could do more than constant number of layers. Well, the reason is that they use computational primitive, and therefore each layer had some computational blow up in the complexity. So they could afford only to apply it for constant number of layers, and we know that with constant number of layers, you can only compute approximate majority. Now, if you compare it to our solution, then it seems that at first that we have a one-shot solution, right, that uses T out of N leakage resilient MPSS. But actually, when you open the box, you see that implicitly, when we construct this information theoretic threshold MPC, we rely on a monotone circuit for exact majority. And the reason that we can do exact majority, and this exact majority is exactly what allows us to do like the full amplification result. And the reason that we can implement this exact majority function is because we allow ourselves to have a circuit of logarithmic depth. And why can we use the logarithmic depth circuit? Because we use information theoretic primitives. Right? And the blowup of such a primitives is typically constant. This is the case in our solutions, and therefore we can afford to do it logarithmically many rounds or levels. So this is perhaps an unexpected benefit of the use of information theoretic cryptography. Thank you.
This concludes the session. Let's thank the speakers again.